Okay, continuing. So can we predict the behavior of a reaction as we have done previously with rate constants? So let's look at our previous example for y goes to x and then amend it with rate information based on the following. So we're going to say kf equals to 10 per second and kr equals to 1 per second. Those are the things that we calculated above. And our delta G standard was negative 5.9 kilojoules per mole. And this makes our equation for delta G the following, right? Because we're y equals to x, y is the reactant, x is the product. So all we're doing is the same thing we did before for this example, but now we're adding rate information. At x equals to 1000, and we're just going to say these numbers are in millimolarity, and that's why our units for the rates have millimolarity in it. So right off the bat, when we say 1000, the concentration of x equals to 1000, we mean 1000 millimolarity. The concentration of y equals to 1, we mean 1 millimolarity. So 1000 for x and y is 1. So we've calculated delta G for this reaction as we've done previously. Nothing has changed here. It's 11.8 kilojoules per mole, and at 11.8 kilojoules per mole, we have said that the reverse reaction is favored over the forward reaction. So let's plug these numbers in to our V forward and VR equations. So when we plug in y into V forward, we get 10 millimolarity per second. When we plug in x into our reverse rate reaction, we get 10 to the 3 millimolarities per second. And we can see that 10 to the 3 millimolarities per second is a much larger number than 10 millimolarities per second. So the rate of the reverse reaction is faster than the rate of the forward reaction. Now, when we are at x equals to 100 and y equals to 1, rate of the forward reaction becomes the following when we plug in y. And the rate of the reverse reaction becomes the following when we plug in x. Now, the delta G is 5.9 kilojoules per mole, so we're getting closer to equilibrium. Before it was 11.8, now it's 5.9 kilojoules per mole, so we're getting closer to equilibrium. So now the reverse reaction and the forward reaction are getting closer together, and you can see that even though the reverse reaction is still favored because we have a positive delta G, it's not as favored as it was before, because before, if we look up here, it was 10 to the 3, now it's 10 to the 2, whereas the rate of the forward reaction has not changed. Now at 10 to 1 of x to y, when we plug in y here and we plug in x here, you can see that, well, first of all, our delta G is 0. So we're at equilibrium. And you can see that the rate of the forward reaction and the rate of the reverse reaction equal each other, which is what we expect. At equilibrium, the rate of the forward and the reverse reaction equal to each other. And of course, our equilibrium constant is 10. Now, at x equals to 1 and y equals to 1, we have a delta G that is negative 5.9 kilojoules per mole, and we know at a negative delta G that the forward reaction is favored over the reverse reaction, and we plug those numbers in, you can see that, okay, yes, the forward reaction is larger than the reverse reaction in its rate. So the forward reaction is moving faster than the reverse reaction. When we get farther away from equilibrium, because now we're at x equals to 1 and y equals to 10, we have a delta G that's negative 11.8 kilojoules per mole. We can see that the rate of the forward reaction is even larger than the rate of the reverse reaction than it was previously. So the difference is larger. So the forward reaction is moving at a much faster rate than the reverse reaction, and so on. So the farther away you get from equilibrium, the more, like here, we're at minus 17.7 kilojoules per mole. Now the forward reaction has 10 to the 3 millimolarities per second, whereas the reverse reaction is still at 1 millimolarities per second. And so on. So the next one is negative 23.6, and we're going to see a bigger difference, 10 to the 4 millimolarities per second to the V reverse being 1 millimolarities per second. So if the rate constants are known, then K can be calculated by 7. So what was 7? 7 was just this equation right here. The equilibrium constant equals to K forward over K reverse, right? So if you know the rate constants, you can figure out the equilibrium constant. If you know the equilibrium constant and one of the rate constants, you can figure out the other rate constant. Also, before pushing forward, if I know delta G standard and I know one of the rate constant, let's say K forward, I can figure out Kr. Why? Because from delta G standard, I can figure out K, and then I can use this information to figure out Kr. So look back at enzyme catalyzed reactions. We had the following figure for an enzyme catalyzed reaction where delta G standard is much less than 0, as in the reaction is very favorable. So this reaction here, the reason why delta G standard is much less than 0 is because we have always said that going from this right here to this, meaning transforming the substrate into product, is a single arrow. If a reaction is extremely favorable, like ATP hydrolysis, the rate of the reverse reaction will always be so tiny that essentially can be ignored because the K is such a big number. Even when the reaction reaches equilibrium, you have so little reactant left over compared to the amount of product made that you can just ignore it. So in this picture right here, just because this arrow right here, this pathway is for a reaction that is extremely favorable. The figure above is not representative of what actually happens. Here are some of the missing details. The binding of substrate, molecule A, to the enzyme is reversible, and it has its own delta G standard. So this is something that we'll be talking about at the end of this section, binding. Binding also has its own delta G standard. Why? Because you have two states. You have enzyme plus substrate, giving you enzyme substrate. Now this is reversible, so the single arrow is not a good representation. This is actually a double arrow. So E plus S going to ES, that has its own delta G standard. The release of product from enzyme is also reversible with its own delta G standard. When we said E, P, giving us E plus P, the single arrow is actually not representative of what is happening. There's a double arrow here. Okay? And this will have its own delta G standard and its own equilibrium constant. So if we add these details in, we get the following. And we've done this before, but we're going to do it again. E plus S gives us ES. And since this is a very favorable reaction, we're going to have a single arrow for the transformation to product. And then we have this. So this part right here has a delta G standard and a K. This part right here has a delta G standard of its own and a K. The reaction has its own delta G standard and its own K. And this delta G right here and the K is just delta G standard of the reaction, the chemical transformation that we've been talking about so far. So what would the enzymatic pathway look like for a reaction that is either slightly favorable or slightly unfavorable? So let me go back to what I was trying to say previously. Let's look at a reaction like ATP hydrolysis. ATP hydrolysis plus H2O gives me ADP plus inorganic phosphate. This has a delta G standard that is much less than 0. And a K that is much bigger than 1. So for a reaction like this, having a single arrow is fine. Why? Because the reverse reaction is so tiny compared to the forward reaction that even when you reach equilibrium, there is so much product compared to reactant. So at equilibrium, because K is such a big number, that you can basically ignore that little bit of reactant that's left over. Okay? So we put a single arrow because we say this reaction goes to, well, this is typically the language used. And I don't like this language, but you might have heard it before, that this reaction goes to completion. What they mean by that because the reaction is so favorable that almost all of the reactant, except for a very tiny little bit, will be turned into product when the reaction reaches equilibrium. Because completion for a reaction is always equilibrium. That's why I don't like that language when they say this reaction goes to completion. Completion is always when the reaction reaches equilibrium, but for a reaction like ATP hydrolysis, when the reaction reaches equilibrium, there's so little reactant left over, almost all the reactant has been turned to product. But there are many reactions where, for example, A goes to B, where the delta G standard might be a little bit less than 0, K is slightly larger than 1, right? Like the one that we talked about previously, our example of Y goes to X, where delta G standard was a negative 5.9 kilojoules per mole and the K was 10, right? So for those type of reactions where it's slightly favorable or slightly unfavorable, then what happens is when we're looking at the enzymatic pathway, we have to put in something else. So here we are, we have our E plus S, and we have our double arrow for this. But now this thing, we put a double arrow here too, because the reaction, depending on the concentrations of substrate and product, it could either favor the forward or it could favor the reverse reaction. And then, of course, we have this. So it's very important. Why are we talking about this? It's very important to know that in the case of many reactions in the cell that are not very favorable, they fall into this category of neither favorable nor unfavorable, meaning that their K is close to 1, maybe a little bit higher or a little bit less than 1. The delta G standard is not that big or not that small, that the reaction, even when it's being enzymatically catalyzed, it can go in the reverse where EP is turned into ES instead of ES being turned to EP, depending on those concentrations. An enzyme will not specifically catalyze the forward reaction only.